In this short little video, I want to give you a demonstration of absorption and fluorescence, so that some of the concepts we've covered in the fluorescence lecture become clear. So what I have here is a solution, a dye solution. It's a dye called rhodamin 6G. It's a very common dye, and it fluoresces. And what I wanted to show you is that I have a green laser beam here. I don't know whether you can see this on my hand, so perhaps we can go on to the close-up shot. And what I'm going to do is I'm going to pass that laser beam through the bottle here, and then you observe what you see. So let me just put these out of the way. These are the samples here, so you can see what's going on. So here's my dye solution, and I'm going to pass the laser beam now from this side through the bottle, and you can watch what happens. So what you see on the camera is that the incoming intensity, I0, goes through the sample, it gets absorbed, and you see the beam is disappearing as it goes through the bottle here. The bottle may be 10 centimeters in diameter. And you can see there's hardly anything coming through that beam here. So if I put the screen on the side, let me just take the bottle away. Here you see the laser beam. I put the bottle in. You see the absorption. Nothing comes through. So the light that you see coming towards you, this bright beam that goes through the sample, that is fluorescence. So the green light of the laser drives the transition up from the lower into the upper excited electronic state, and then from the upper state there's some collisions and so on, some vibrational energy transfer, some dipole reorientation. So what we get is redshifted light. So the fluorescence light here will be less energetic than the excitation light, and it is absorbed. And you can see two things. First of all, whilst it would be impossible in this sample to do an absorption measurement because the beam has been absorbed. There's nothing coming through. So you cannot do I over I0. The transmission is 0. So this sample is clearly too concentrated for you to see it. What you can nevertheless still see is a very strong fluorescence signal all the way across the sample. Of course, where all the photons have been absorbed from the beam, then of course there's no signal from fluorescence either. But you get the idea. So even at these high concentrations, you can still get a very strong signal, of course, in fluorescence, but not in absorption. Let's take another sample. Let's look at this sample here. This sample is now a much more dilute sample of the same dye. Again, it's rhodamin 6G. Let's do the same thing. I have my laser beam. It passes onto my card, and now I'm putting this into the sample. Now what do we see? Actually, you see that this sample is sufficiently dilute that the beam is coming through. In fact, if you measured the intensity here, it's hardly diminished. You can see why absorption again would be hard to do. Comparing this intensity with this intensity, or the intensity here and the intensity there, with one another, there isn't enough absorption for you to do a reliable measurement. Maybe you have 100 photons, 100% of the energy going in here, maybe 99 coming out. Hard to measure, just a 1% difference. On the other hand, again, the fluorescence signal is extremely strong all the way through. And if you know what the quantum yield is inside the sample, you can work out what the concentration inside the sample is. Let us now go to this sample here. What is this? So I do the same thing. Here's my laser beam. You see it's passing it's going across to my screen here. I put this in, and actually nothing happens. You see nothing at all. The beam just passes through. What's happening here? This is just water. There's nothing in it, so you can't see anything. What about this? Same thing again. This looks exactly the same as water. Let's put the laser beam on, and look at this. The beam passes through, of course, without any absorption, because but in fact this contains a very dilute concentration of rhodomine 6G. Again, the solution far too dilute for you to measure this in absorption, but the fluorescent signal is extremely strong. And the reason is that we have the fluorescence appearing on a zero background. There is only signal when we drive the transition. So you see very strong absorption, very strong fluorescence. Light beam is absorbed, although most of the photons go through. The sample is still fluorescing very hard. I would like you to think what the word transparency means. In the region where I'm exciting this fluorescence through the sample is transparent. And I would like you to tell me why the sample is transparent. Why is that the case in that region? Let me now turn to this laser. This is a red laser. And so if I pass this laser through here, nothing happens. The laser just goes straight through, and I don't see any fluorescence. Why is that? Tell me about why that may be the case. I can go back, in fact, to this highly concentrated sample. And look at this. Even in this super highly concentrated sample, this beam goes straight through. Whereas with the green beam, it was totally absorbed. It doesn't pass through. Why is that the case? I would like you to do the following. Let us assume that let us assume we have a dye solution like this, and let us assume that there's some green light still coming through, and I'm going to the blackboard over there, not the blackboard, this fluorescent light board. Let me go to that, and let me just write this down. So why don't you calculate what the concentration of the sample is? So we said that the bottle has a diameter L. The absorption path length, let's say, is 10 centimeters. And let's assume the transmission that we measure in that in the dye solution, in one of the dye solution, is 10%. And let us assume further that the extinction coefficient is equal to 100,000 per mole cubic decimeter per centimeter. Can you tell me what the concentration of dye molecules is in the solution? And if the quantum yield, if the fluorescence quantum yield is 0.9, could you work out the number of photons? What is the number of fluorescence photons emitted if I naught is equal to 1 milliwatt? So in other words, we put a power of 1 milliwatt I naught into the sample. 90% of that will be absorbed because the transmission is 10%. I have a fluorescence quantum yield of 0.9. How many photons will be emitted per second for this system? I'd like you to work that out in fluorescence. And with that, thank you, and we'll finish this lecture.